Okay, welcome back. This is our second edition. This is section 5.2, confidence intervals using normal distributions. Let's just briefly recap what we learned in section 5.1. In that section, we saw that in many situations, Bootstrap and randomization dot plots form bell-shaped curves, and that these curves can be approximated by normal distribution curves. Recall that a normal distribution curve is characterized by two parameters, the mean, mu, which is the axis of symmetry for the curve, and the standard deviation, sigma, which specifies how concentrated that curve is about its mean. The smaller the value of sigma, the more concentrated the curve is about its mean value. To associate a dot plot with a normal curve, we simply identify the mean of the dot plot with mu and the standard error of the dot plot with sigma. We use this association between dot plots and normal curves to conduct hypothesis tests. That was what we did at the very end of section 5.1. We saw that we could calculate a p-value by counting dots on a dot plot, or by association, computing an area under a normal curve once we made that association. Okay, in this section 5.2, we're going to show you how to use kind of the same idea, how to use normal distributions to help us find confidence intervals. Now, this is the outline of things we're going to cover in section 5.2. We're going to kind of review from earlier in the semester. We're going to review bootstrapping confidence intervals. And then at the same time, I'll show you how we can use this association to normal distributions to get essentially the same calculation from a normal distribution. Then I'll show you how the standard normal distribution can be used to help us understand how to form confidence intervals. And then we're going to put all of it together. I'm going to work out some examples where I'll use the whiteboard so you can kind of see these examples develop in real time. And then finally, at the very end, we want to look at the margin of error through two different lenses. One is, how is the margin of error affected by our confidence level? And then anticipating what we're going to do in chapter 6, how is the margin of error affected by our sample size? So we're going to want to look at margin of error in a little bit of detail at the end of this section. Okay, bootstrap confidence intervals. Let's review a typical problem that we would have done in a prior section. Okay, let P sub A and P sub T be the proportions of adults and teens that send and receive text messages respectively. So we're thinking of these as parameters within the populations of adults and teens. A study of 2,252 adults aged 18 or older found that 72% of cell phone users send and received text messages. Thus, the sample proportion for adults is 0.72. A study of 800 teens aged 12 to 17 found that 87% of the teen cell phone users send and receive text messages. Thus, the sample proportion for the teens is 0.87. In each case, use bootstrap sampling to develop a confidence interval for P sub T minus P sub A at each of the specified confidence levels. So we're going to use stat key here, and we're going to develop confidence intervals for the difference in these proportions across these three different very kind of typical confidence levels: 95%, 90%, and 99%. So let's go to stat key. And I want you to try to do this with me. So if you have to pause the video and try this yourself, please do that. Get in the habit of kind of working along with me on these problems. So we're going to do a confidence interval for the difference in proportions. And it's going to preload some data. And what we're going to want to do is make sure that this is the correct data set. This is text messages by age. And this is it. So we've got our data all in there. And this is doing it in the order of teens minus adults, which is exactly what we want. So we can kind of see that the difference in our sample proportions is 0.15 when we do teens minus adults. Now all we want to do is develop several thousand bootstrap samples. Let's just do 5,000 bootstrap samples. And if we remember, we can develop confidence intervals at the 95, 90, and 99% confidence level by simply having stat key count for us. All it's going to try to do is carve out the middle 95% of these dots, and we can kind of just look down here at the bottom of the screen, and we have our confidence interval going from 1.21 to, 0.121 to 0.180. Now, this is just by counting dots. We could have, in the case of this 95% confidence interval, just as well have taken the best estimate for that difference, which was 0.15, and then taking 2 times the standard error, and that would have given us essentially the same result. So in the case of a 95% confidence interval, we have this other method that we could use. Now, that method is not available to us for 90 and 99% confidence intervals. All we can do is go in here and edit this, and we can carve out the middle 90% of the dots, and that will leave us with a confidence interval extending from 0.125 to 0.176, and at 99%, we would have our confidence interval going from 0.111 to 0.190. So stat key simply counts dots on this Bootstrap dot plot and carves out the middle 95, 90, or 99% as needed. Okay, now we'll come back to this picture in just a second, but just let's go back to the slides here real quick. Now, here's what we're going to do. We've just done some work using a dot plot, but now I want to show you how you can effectively do the same work using an associated normal curve. So as we saw in section 5.1, if the Bootstrap dot plot of a statistic is bell-shaped, then this dot plot can be approximated by a normal distribution curve with parameters that are drawn from the dot plot. So we just let mu be the sample statistic or best estimate. That's essentially the axis of symmetry for a dot plot. And we let sigma be the standard error or the SE of the dot plot. If we grab that mu and that sigma, and they become the parameters of a normal distribution, then calculations that can be done on the dot plot can be done analogously on that associated normal distribution. So what we want to do is ask ourselves, what normal distribution curve would we use to approximate that text message data that we just saw? And can we use the associated normal curve to construct those 95, 90, and 99% confidence intervals? So let's go ahead and take a look. If we go back to stat key, the 2 pieces of information that we're going to want to pull out of here are the mean of the dot plot, that's the 0.15, and the standard error of this dot plot, which is up here, and it's 0.015. So we want to write those 2 pieces of information down, because we're going to leave this, and we're going to go down to theoretical distributions, normal, and we're going to edit the parameters here so that they can reflect our mean, which now is 0.15, and the standard error or standard deviation should be 0.015. So those are parameters that we pulled right out of the dot plot, and we can drag them into our normal curve. Now, the idea is this normal curve that we've now created stands in place of, or does essentially the same work as that dot plot. So if I want to carve out the middle 95% of the area under this normal curve, that will give me an interval which should be the same as, or nearly the same as, carving out the middle 95% of the dots. So let's do a 2-tailed calculation. Here's our middle 95%. It extends from 0.121 to 0.179, which is very, very close to what we had when we worked with the dot plot. I can change this to the middle 90%, and that will have an interval that extends from 0.125 to 0.175, which again agrees very well with what we saw before. And if I want to carve out the middle 99%, I can do that as well. And once again, we're getting a range from 0.111 to 0.189, which again agrees very, very well with the dot plot that we worked with. So this analogy between working with dot plots and working with their associated normal curves continues to work well here in the realm of bootstrapping. It works just as well as it did in the realm of hypothesis testing. So that's the takeaway from this. So we can do this kind of work not only with the dot plot, counting dots, but we can do it with a normal distribution that's tuned to that dot plot, instead calculating areas. All right, let's try this again just to make sure we've got this technique down. And I encourage you to try this along with me. In fact, if you want to try to do this before I do it, go ahead and give yourself a chance to try this. We're going to try to do this through the two different methods. One is literally counting dots, working directly with the dot plot, and the other is extracting the mean and the standard error from that dot plot and then working with the associated normal distribution. But let's take a look. Let rho be the correlation between distance and commute time in Atlanta. The commute distances and times were collected for a random sample of 500 commuters in Atlanta. Use this data to find a 90% confidence interval for a rho in two different ways. Method one is to use the Bootstrap dot plot and compute the confidence interval directly from that using StatKey's dot counting method. And the other is to use an appropriate normal distribution function to compute the confidence interval, the same 90% confidence interval. So let's go ahead and go to StatKey. We're doing a confidence interval for a correlation. And this is for the commute times in Atlanta. And here we can see our sample. We can see that the data looks highly correlated. The distance and time are highly correlated, not surprisingly. That's not really what we're trying to do here. We're trying to get a confidence interval for the correlation. So let's generate several thousand samples. Now, it is interesting to note in this case that this curve is bell-shaped, but it does seem to have this tail that's pushing off to the left. It is a little bit skewed to the left. Now, let's see what effect that has. I don't think the effect is going to be that great. All right, now, if I want to compute a 90% confidence interval, I'm asking StatKey to tell me where the middle 90% of the data lie. And it says that it's going to extend from 0.74 out to 0.859. I'm going to write that down for comparison purposes. All right, that's using the counting dots method. Now, we want to pull two things out of this dot plot so we can do it by normal approximation. So we're going to take the mean, 0.806. We're going to write that down. And we're going to grab the standard error of 0.037. All right, we want to pull those two pieces out of this Bootstrap dot plot. And now we're going to do it from a different perspective, and that is by replacing that dot plot by a normal curve. We're going to edit these parameters accordingly. We're going to have a mean of 0.806. And we're going to have a standard error of 0.037. Okay. And now this curve that we've created stands in place of that dot plot. And we can ask the same kind of question, though. We can say, where is the middle 90% of the area? And we can see for our standard normal curve that that's going to extend from 0.745 out to 0.867. Now, in our dot plot, this left endpoint was 0.740, and this right endpoint was 0.859. And you can see it's not perfect. It's an approximation. This standard normal curve is approximating that dot plot, so we're not going to get absolute perfect agreement. But for all intents and purposes, this is very close. This is close enough for most applications. So once again, we can see this relationship between using the dot plot directly and counting dots, and using the associated normal curve and calculating areas yields essentially the same result. Okay. Now, this is where some theory comes in, and it's really, really important to develop this theory. So pay special attention here and try to really dig in at this point. All right, let's see where we are, and let's see where we're going. If you remember, early in the semester, if we wanted to develop a 95% confidence interval for a parameter, we had a really simple rule that we could use. We could pull a sample, a random sample out of a population and get our best estimate for that parameter. So for example, if we were trying to get a confidence interval for a mean, we would get a sample mean. If we were trying to get a confidence interval for a proportion, we would get a sample proportion. There was some way that within that sample, we could find a best estimate for that population parameter. That formed the center of our confidence interval. The radius of our confidence interval, the so-called margin of error, we could get by just taking 2 times the standard error. We could read that right out of our Bootstrap dot plot. And this gave us a really simple way. This didn't even involve counting dots. This was in some sense thought of as a universal law. It said best estimate plus 2 times the standard error will always give you a 95% confidence interval. Now the problem that we saw back then was that if this confidence level changed to 90% or to 99% or to 80%, whatever, this rule for the margin of error was no longer valid. And so what we want to do now is show how we can develop new rules that so no matter what confidence level we're given, there's always an appropriate multiplier here. We're looking to replace this number 2 by a multiplier that's tuned to the confidence level that's being given to us. So for the 90% confidence level, there will be a multiplier here in place of the 2. For the 99% confidence interval, there will be another multiplier here that will stand in place of that 2. Okay, so our goal in this next section of this section, the next subsection, if you will, is to develop some theory to extend this formula to other confidence levels. So this general rule will be best estimate plus or minus z star times the standard error, SE, where the value of z star is determined by the confidence level. So we're looking to find a general rule to replace this simple rule that we were using earlier in the semester. Okay, so we have to dig in a little bit into some of the theory here to see how this comes about. All right, now, the textbook doesn't develop this terminology, but I do think it's helpful, so I'm going to ask you to kind of work with me on this. I think it does clarify some things to have this terminology, so let's go with this. So let A be a number, and that number should be between 0 and 1. The number z sub A is the value such that A units of area are situated under the standard normal distribution curve to the right of z sub A. Now this is a lot to wrap your mind around, so let me see if we can see this, take this text and unpack it in this picture. So suppose your goal was to find the cutoff that put A units of area to the right and 1 minus A units of area to the left in a standard normal curve. So for instance, this might be 10% on this side and 90% on this side, or 5% on this side and 95% on this side. So suppose you had a target here. You wanted 5% or 10% on the right. What cutoff would give you that proportion or that percentage of the area on the right? That number is called z sub A. All right, now this is phrased in terms, not in terms of percentages, but in terms of decimals. So if this was 10% of the area on this side, we would call that z sub 0.10. If this was 5% of the area on this side, we would call that z sub 0.05. It's the cutoff that puts that exact amount of area on the right. Okay, so that's the idea behind z sub A. Now, let's get a little bit comfortable with this by computing some of these. So we're going to use StatKey to do this because StatKey is perfectly set up to do this. Let's verify, let's do this one first. Let's verify that z sub 0.05 is equal to 1.645. Okay, so let's go to stat key. We're going to go to theoretical distributions, normal. Now, we're always, in this context, when we're working with these z sub a values, this is always in the context of a normal with a mean of 0 and a standard deviation of 1. We're always working with the standard normal, so there's no need to edit the parameters. Now, here's what we have to picture. We have to picture a cutoff value that's going to put 5% or 0.05 in this right tail. So it's a right tail calculation. We want 5% in that right tail, and that's telling us that that cutoff occurs at 1.645, and that's why z sub 0.05 is 1.645. Let's do the z sub 0.025 calculation. We want 0.025 in the right tail, and that cutoff is 1.96. And then finally, if we want z sub 0.005, we have to find 0.005 units in the right tail, and that will happen if we use a 2.576 cutoff. All right, so hopefully that's making sense. That given a value, I've been calling it A, given a value here, we want to find that value or that area in the right tail, and this tells us where the cutoff for that right tail should be so that that amount of area sits in the right tail. Now, hopefully you're noticing that as this value goes from 0.05 to 0.025 to 0.005. So in other words, this A level is going down, right? That these values are going up, they're increasing. Now that stands to reason because we're putting less area in the right tail, so we have to go out farther to find that corresponding cutoff. So as this level is going down, these numbers are going up. All right. Now, let's test your understanding of the terminology. This is going to be an important moment for you here. We're going to use the z sub a terminology. Using the z sub a terminology, describe the interval that contains the middle 80% of the area under the standard normal distribution curve. Now, I'm not going to reveal the answer to you first, but let's talk through this. We've got our standard normal curve. We want to construct the interval, so I want these two endpoints. I want the left endpoint, and I want the right endpoint, and I want to contain 80% of the area here in the middle. Okay, now, I don't want the numbers. I just want you to think about what z sub a values you'd attach to the left and to the right to describe this. All right, so pause the video here and give yourself a chance to think about what you would do. Think about what z sub a is doing and see if you can get an answer here. Okay, so hopefully you've thought about this and you've realized that if I want to contain 80% here in the middle, that remaining 20% of the area has to be contained equally in the right tail and the left tail. So I need to have 10% of the area over here and 10% of the area over here. Now, the z sub a's are always phrased in terms of right cutoffs, and so we'll want z sub 0.10 on this side, and then we can just reflect that and have negative z sub 0.10 on this side. So our interval should extend from negative z sub 0.10, that's our left, and z sub 0.10, that's our right cutoff. Now, when you have stat key do the calculation, it shows that that goes from negative 1.282 to 1.282. And there's the picture that goes along with it. There's our 80% in the middle, and our two 10% carved out into the left and to the right. So if we want to get a middle 80%, we have to think of the residual part, the 20%, being divided equally into the right and to the left tails. Okay, let's formulate a general rule. Here's a general rule. Let alpha be a number between 0 and 1. The interval that contains the middle 1 minus alpha proportion of the area under the standard normal distribution curve is the interval that extends from minus z sub alpha over 2 to z sub alpha over 2. Now, this seems very backwards to describe the middle 1 minus alpha proportion of the area. All right, so let's think about what's going on here. This is saying if I want the middle 90%, I have to think of that 90% as 1 minus alpha, right? That means alpha is equal to 10% or alpha is equal to 0.1. Then I have to take that 0.1 and I have to divide it into a right side and a left side by taking it into two pieces. I have to cut that in half. So I have to take that remaining 10% and put half of it over here, that's 5%, and the other half over here, that's 5%. Then I have to find the cutoffs that correspond, well, the cutoff that corresponds to that 5%, and so I have to find z sub 0.05, and then I can take its negative. So this is describing the process by which we can carve out a middle 80% or a middle 90% or a middle 99%. The key here to understand is that I take the part in the middle, I take what's left over, and I divide it equally into the right and to the left tails. And so I think, and this is you'll see this is very commonly used, you describe the middle as some fraction removed from 1, removed from the whole, and then this gives you an easy way to describe where those cutoffs are going to occur. All right, I think if you just work with this a little while, you'll get comfortable with it. I wouldn't worry about this too much. It does seem like it's a rather convoluted way of explaining something, but it does end up being helpful. Okay, so our next goal is to take this simple rule for carving out the 1 minus a middle units of area under a standard normal curve and develop a rule for non-standard or for general normal distribution curves. Okay, so here we go. Consider a normal mu sigma distribution curve. The interval containing the middle 1 minus alpha proportion of the area under this curve is mu plus or minus z sub alpha over 2 times sigma. That is an interval that extends from mu minus z sub alpha over 2 times sigma to mu plus z sub alpha over 2 times sigma. So the important thing to remember here is that this z sub alpha over 2 is a number that is going to be computed directly from whatever middle proportion we want. So if we want the middle 90% of the area, that's going to be alpha equal to 10% or 0.1, and we're going to go with a z sub 0.05 here and a z sub 0.05 here. These two numbers, the mu and the sigma, are going to be numbers that we are getting directly from the parameters of the normal. So once we have the mu and the sigma, and once we know the middle that we want to carve out, these three numbers are known to us, and we can easily construct this interval. So working with this is going to be actually rather simple once we get comfortable with this technique, but conceptually we have to kind of understand what's going on here. Okay, let's first of all test what's happening here. If I go back to this scenario here and I set mu equal to 0 and sigma equal to 1, when I go down to this interval, mu is going to be equal to 0, so this is going to drop out. Okay, and if sigma is equal to 1, this is just going to be multiplying by 1 here and here, and this entire interval will just reduce to minus z sub alpha over 2 to z sub alpha over 2. In fact, we're just back to here. So this formula is working in the case where mu is equal to 0 and sigma is equal to 1. So in some sense, we should think of this as the more general formula. This works for all normal distributions. Okay, now, why is this working? Well, I don't really want to, you don't really have to get that deep into the weeds on this unless you want to. But the general idea is anytime I want to calculate an area under a normal curve across an interval, I can always transfer that problem to calculating an area under a standard normal curve, provided that I standardize the two endpoints. So if I take this left endpoint and standardize it, and I take this right endpoint and standardize it, I can reduce the problem down to calculating the area under a standard normal curve with those two new endpoints. Now, what would it mean to standardize this right endpoint? That means I would take this right endpoint, subtract the mean, and divide by the standard deviation. All right, let's take a look at what that process would look like. If I take that right endpoint and I subtract the mean and divide by the standard deviation, in the numerator here, the subtraction of that mean will just leave us with z sub alpha over 2 times sigma. But when I divide by sigma, that cancellation will just leave me with z sub alpha over 2. If I do the same kind of calculation with the left endpoint, if I standardize the left endpoint, you'll see that it standardizes to z sub alpha over 2. So what I'm saying is that to calculate the area under this normal curve over this interval is the same as calculating the area under a standard normal curve from this left endpoint to this right endpoint. Now, the area under the standard normal curve over this kind of interval is 1 minus alpha. That's exactly how these cutoffs were designed to work. This cutoff leaves alpha over 2 units of area still to the right, and this cutoff is going to leave alpha over 2 units of area to the left. That means in the middle, the part that sits over this interval contains 1 minus alpha units of area. All right, now, I'm not going to test you on your understanding of how this comes about, but I certainly do want us to be able to work with this idea. So, okay, so let's put this method to the test. Consider a normal distribution curve with mu equals 50 and sigma equals 2.3. In each case, find the indicated interval using the mu plus z sub alpha over 2 times sigma method. So we're going to use our cutoff method here. All right, so let's take a look at this first problem. Find the interval containing the middle 95% of the area under this curve. So we're picturing this curve, this normal curve with a mean of 50 and a sigma of 2.3. So we're picturing this curve and we want to think, how would I cut out the middle 95% of this area? Which interval would carry that middle 95%? Likewise, which interval would carry the middle 90%? And which interval would carry the middle 99%? All of these intervals are going to be formed using this method. We just have to know what the appropriate cutoff is for each of these indicated intervals. So let's go ahead and think about this. I've set up some standard z cutoffs up here. So z of 0.05, z of 0.025, and z of 0.005 are these three numbers. These are the numbers we actually calculated earlier when we were first introducing this idea. Okay, in all of these cases, the mean mu is 50 and the sigma is 2.3. So all we have to do is understand that when we're trying to carve out the middle 95%, that's going to leave 5% out. That 5% is going to be half on the right and half on the left tail. That's 2.5% or 0.025. So the cutoff that's appropriate for this calculation is this 1.96. So we simply take 50 plus or minus 1.96 times 2.3. We work out the margin of error. That's going to be the product of these two numbers. That's 4.508. We subtract it, we add it to 50, and that gives us this interval from 45.492 to 54.508. That interval for this particular curve is going to carry 95%, that middle 95%. Now, as I move from 95% to 90%, the only thing that changes is this multiplier. And how does it change? Well, I want the middle 90% that's going to leave 10% out, 5% on the right, 5% on the left. That's z.05. That's a 1.645 multiplier. The 1.96 gets traded off for the 1.645. The product of these two is the new margin of error. And when I subtract and add that margin of error to the center 50, I get this corresponding interval. And then finally, if I want to construct a 99% middle that leaves 1% out, that's 0.5% in the right and 0.5% in the left. When I think of that 0.5% as a decimal, that's 0.005. So my 0.005 cutoff is going to be 2.576. That multiplier gets exchanged here for 2.576. It's now 50 plus or minus 2.576 times 2.3. That margin of error is 5.9248. And I get 50 minus that and 50 plus that to get this new interval. Now, just so we can make sense of this, let's just think about what's going on here and just let's have StatKey do the same calculation for us just so we can kind of understand how this method is in effect doing the same thing that we could get by going directly to StatKey. So if we go to StatKey, theoretical distributions, normal, if I type in, if I edit these parameters and type in the 50 and the 2.3, let me double check that those are the parameters. Yes, they are. So if I type in the 50 and the 2.3 for the mean and the standard deviation, and I ask it to do a two-tailed calculation and to give me the middle 99%, it's going to give me an interval that extends from 44.076 to 55.294, so roughly 44 to 56. And that's exactly what we're seeing here. All right. Notice that we did this calculation here, this 99% calculation, just using some theory, right? We used some theory about the standard normal to give us this multiplier, and we grabbed these two parameters from the normal distribution that we were given. And from that, using just a little bit of multiplication and addition and subtraction, we're able to work out this interval. All right, now, we want to put all of this together. Now, remember, finding a confidence interval, it is essentially carving out a middle, either a middle set of dots, a middle proportion of dots, or a middle a piece of area under a normal curve. So we're ready now to kind of think about how we could use the theory that we've been developing to help us develop confidence intervals, right? Because it is just essentially the same kind of calculation. How do we get a middle unit of a middle proportion of dots or a middle chunk of area under a normal curve? Okay, so let's put it all together. This is about finding a 1 minus alpha confidence interval for a parameter. So here's the setup. Suppose we want to build a 1 minus alpha confidence interval for some parameter within a population. So maybe it's a mean. We want to find a mean parameter in a population. All right. Collect a random sample from the population. Let best estimate be the value of the corresponding sample statistic. So that could be a sample mean from a random sample. Suppose that the Bootstrap dot plot of the sample statistic is bell-shaped with a standard error SE. So let's identify mu and sigma. Let mu and sigma be the values of best estimate and SE respectively. So at this point, we're imagining there's a dot plot for that sample statistic, and then there's a corresponding normal curve, right, that we get by extrapolating from the dot plot the mean and standard error. So we've got our dot plot, we've got our normal curve, right? The 1 minus alpha confidence interval for the parameter is best estimate plus z sub alpha over 2 times SE, all right? So what we effectively have here is an extension of the formula that we used for 95% confidence intervals, right? For 95% confidence intervals, we said it was always our best estimate plus or minus 2 times SE. And this is saying, well, if you have a more general confidence level, if you have a 1 minus alpha confidence level, that number 2 should be replaced by some kind of z cutoff. All right? So this extends that kind of general rule that we saw before. All right. Now, why is this working? Well, as we said before, mu and sigma correspond to the mean and SE of the Bootstrap dot plot, right? We know that the interval mu plus or minus z alpha over 2 times sigma carries or contains the middle 1 minus alpha units of area under that normal distribution curve. By approximation, that same interval is going to carry the middle 1 minus alpha proportion of the dots in the Bootstrap dot plot. That means that this interval is giving us the left and right endpoints of the 1 minus alpha confidence interval. But that is, mu is the best estimate and sigma is the SE. So another way of reading this is best estimate plus or minus z alpha over 2 times SE is our 1 minus alpha confidence interval for the parameter. All right, so this gives us a natural extension of our best estimate plus or minus 2 times SE to other confidence intervals besides the 95% confidence interval. All right, let's work some examples. Now we'll read these together on the slide, but then we'll work them out on the whiteboard so you can kind of see them develop in real time. I think it's going to be easier to see these answers develop on the whiteboard rather than just have them appear on the screen. So we'll do a little mixture of reading from the slides and working on the whiteboard. But let's take a look at this problem first. Reese's Pieces are a candy covered in candy shells that are colored yellow, orange, or brown. Let P be the true proportion of Reese's Pieces that are colored orange. So suppose we wanted to know, as these things are coming out of the factory, what proportion of Reese's Pieces are orange colored. Well, one way of getting our hands on that would be to randomly sample. In this case, we did a random sample of 150 Reese's pieces, and they contain 72 orange pieces, yielding a p hat of 0.48. The Bootstrap dot plot of p hat has a standard error of 0.04. All right. In each case, use a normal distribution to find the indicated confidence interval. So we want to find a confidence interval at 95%, 90%, and 99%. So let's go to the whiteboard and see that calculation develop. All right. All right, so for this first problem, we're going to want to do a sequence of confidence intervals for proportion P. Now, what is that proportion? P is the proportion of orange candies in Reese's Pieces. And what do we know? That when we did a sample, we got a p hat of 0.48, and when we looked at the bootstrapping dot plot for that, we found that the standard error in that dot plot was 0.04. Now, our first goal is to find a 95% confidence interval for P based on this information. So when we want to find a 95% confidence interval, let's just think this through. We want to find a 95% confidence interval. And that means that the alpha, that the part that's left over, is 5%. And that means that half of alpha is 2.5%. Which corresponds to 0.025. So when we're trying to construct a 95% confidence interval, we're going to use a cutoff of z of 0.025. We're going to use this 1.96 for our confidence interval. So our confidence interval, our 95% confidence interval, is going to use a z of 0.025. And so just using best estimate plus or minus our cutoff times the SE, we end up with a confidence interval which is going to be equal to 0.48 plus or minus the cutoff 1.96 times the Z, times the SE of 0.04. Now these two terms together, the 1.96 and the 0.04, together give me this so-called margin of error. Let's compute that first. That margin of error is 0.0784. So we're going to have 0.48 plus or minus 0.0784. When I do these calculations with this calculator, I like to store that margin of error so that it's easy to finish up the problem. What we want to do now is finish this up by giving the endpoints of our confidence interval based on adding and subtracting the margin of error from that center. So when we do that, we're going to end up with 0.48 minus the margin of error, which is rounding going to give me 0.402, and 0.48 plus the margin of error, which is going to be 0.556. Okay? So that's going to be my first confidence interval. 0.558. And that's going to be my 95% confidence interval for P. Now, I'm going to erase some of this so I can do my next calculation, but I do want to retain this confidence interval here, so I'm going to erase some of this. We remember what the value of P is. Now all that's going to change, the P hat and the SE are going to be the same. All that's going to change as we move from problem to problem is our confidence level and hence our Z cutoff. So this will be the only part that changes as we move from the 95% to the 90% to the 99%. So what we'll see is a succession of calculations where this is the only piece that's changing. So let's take a look at what happens. Let me erase this. Let's look and see what happens when we work at a 99% confidence, or excuse me, at a 90% confidence. So at 90% confidence, the part that's left over, the residue, is 10%. So our alpha is 10%, and half of alpha is 5%. And as a decimal, that's 0.05. And so we'll be working with this cutoff, the 1.645 cutoff. So our confidence interval is simply going to be the same best estimate, the 0.48 plus or minus 1.645 times the SE, which we used before, which is going to be the 0.04. That margin of error, let's calculate that. The margin of error is 1.645 times 0.04. That margin of error is equal to 0.0658. And that's going to give me an interval that extends from 0.414 out to 0.546. So when you add and subtract that margin of error from the center, you're going to get this interval. All right, so let's record that one. That's our 90% confidence interval. And let's do one last calculation. This one is now going to be at the 99% confidence level. Now at 99%, we know that the residue, the alpha, is 1%. Half of alpha is 0.5%. And then moving the decimal place, we can see that that's equivalent to 0.005. And so we'll be working with this 2.576 cutoff value. So our confidence interval is nearly the same thing. Formally, it's center or best estimate plus or minus, now we're using this cutoff value, 2.576 times the same SE that we've been working with consistently in this problem, and that's going to give us 0.48 plus or minus the margin of error in this case. Let's do it 2.576 times 0.04 equals 0.10304. And once again, just as before, by adding and subtracting that margin of error, we'll get an interval that extends from 0.377 to 0.583. That's our 99% confidence interval. So in the language of confidence intervals, we would say we are 99% certain that this interval from 0.377 to 0.583 covers or contains the true proportion of orange candies manufactured by Reese's Pieces. All right, so let's put that together with the other confidence intervals that we contain, because we'll want to make note of one thing while we've got all this information in front of us. So our 99% confidence interval is going to extend from 0.377 up to 0.583. Now let's talk about between these three confidence intervals. Let's rank them by precision. Which of these intervals is actually making the most precise statement? And the way to gauge precision is just to look at the length of the interval, or to think about it in terms of margin of error, right? They're going to be saying exactly the same thing. So which of these intervals is narrowest and is giving us the most precise statement about the true proportion P? Well, it's this one here. This one we would rank as the most precise. Which one is the next? Which one has the next best level of precision? Well, it's this one here. And the last one, the one that is the least precise, is this 99% confidence interval. So we can see actually that as the level of confidence goes up from 90% to 95% to 99%, the level of precision is going down. We're making less and less precise statements. We are making more confident statements, but we are making less precise statements. And so that's often the way this works, right? To make more precise statements, you have to give up confidence, all right? To make more confident statements, you have to give up precision. And that's just the nature of the game. Once you've collected your sample, you're always going to have to trade off your confidence level with your level of precision. Okay. All right. Let's move on to the next problem. All right. Here's a second problem that I want us to study. And again, we'll solve this on the whiteboard. This is problem 5.44 from the text. So if you want to look at that problem in the text for a reference, you can find it there. In this problem, a survey of 1,000 air travelers found that 60% prefer a window seat. The sample size is large enough to use the normal distribution, and a Bootstrap distribution shows that the standard error is SE equal to 0.015. Use a normal distribution to find and interpret a 99% confidence interval for the proportion of air travelers who prefer a window seat. So we're going to use our methods that we've developed to find a 99% confidence interval. All right, let's go to the whiteboard. Okay, so this is problem 5.44. We're going to work this one on the whiteboard. And we just have to remember what it is that we're doing in this problem. We're trying to develop a confidence interval at the 99% level for this proportion P, which we're thinking of this as the proportion of air travelers that would prefer the window seat. So let's just say air travelers that prefer a window seat. That's just to help us remember what the context for this problem is. So this is the proportion we're after. Now what do we know? We have a sample that we've collected, and we know that from the sample collected that we know that 60% of the passengers prefer the window seat. And we found that when we bootstrapped this sample, we got an SE of 0.015. Okay? Now we want to develop a confidence interval from P based on this at the 99% level. So if we just go through this calculation, we don't have to do this each and every time, but let's just, as we're kind of learning this, we want to develop a confidence interval at the 99% level. The excess or the residue is 1%. That's what we're calling alpha. Half of alpha is 0.5%. When I treat that as a decimal, I'm going to get this 0.005. So we're going to be working with this cutoff, this 2.576 cutoff. So 99% interval, 99% confidence intervals are going to be using this cutoff value here, the 2.576. Now, it's very easy to finish up the problem. All we have to do is put our best estimate, our cutoff value, and our SE together. So our confidence interval is going to be 0.60 plus or minus 2.576 times the SE, 0.015. And that's going to give us a margin of error of, let's multiply these two together, 2.576 times 0.015. That's going to give us a margin of error of 0.03864. Now when you take that margin of error, add it and subtract it from the center, and I'm going to do a little bit of rounding here, I'm getting 0.561 to 0.639. Okay? And what would we say if we were going to try to describe this to somebody? We would say we are 99% confident that the true proportion of air travelers that prefer a window seat is covered by this interval. And that's all we have to do to finish this problem off. Okay, let's move on to the next problem. Okay, one last problem. In a survey, 17% of the men said they had used online dating, while 14% of the women said they had. Find a 99% confidence interval for the difference in the proportion saying that they used online dating between men and women. The standard error of the estimate is 0.016. A follow-up. Is it plausible that there is no difference between men and women in how likely they are to use online dating? Use the confidence interval from part 1 to answer and explain your reasoning. So let's go to the whiteboard and see how we would work that one out. All right, so we're going to do this one last problem here at the whiteboard. This is problem 5.52. And in this problem, we're being asked to build a confidence interval for a difference in two proportions. So let's take a look at the two proportions that are relevant here. We're going to call one of them P sub m. And this is the proportion that use online dating for the category of, let's say, men, and there's going to be a corresponding P sub f, and this is the proportion that have used online dating for the category of women. Now we're being asked to find a confidence interval for the difference in these proportions. We have to impose a direction on this. We can subtract them in either order, but we'll do it this way. We're going to look at a confidence interval for P of m minus P of f. Now, what's our best estimate for this? Well, when we look at the sample data, we're told that this proportion for men within the sample is 0.17, and within the category of women, it's 0.14, so that gives us a best estimate of 0.013. What's more, we're told that when they bootstrapped this sample, they got an SE of 0.016. All right, so our confidence interval at the 99% level is going to be simply what we get by taking this as the center of our interval. That's our best estimate. plus or minus the cutoff that's appropriate for a 99% confidence interval. Now, we've been down this road several times. We know that when we want to build 99% confidence intervals, we have to use this 2.576 Z cutoff, and then we'll put that together with our 0.016 SE, and this is going to give us our confidence interval. Now, when you work this out, when you calculate the margin of error, add it and subtract it from that center, what you'll find is you get a confidence interval that extends from minus 0.011 up to 0.071. Okay, so that's your 99% confidence interval for the difference in the proportion PM minus PF. All right, so how would we articulate that? We would say we are 99% confident that the difference in PM and PF is covered by this interval. All right, that fulfills part one of the problem. We've got that confidence interval built. Now, the second part of the problem asks us to engage this question. Is it plausible that there is no difference between men and women in how likely they are to use online dating? Use the confidence interval from part one to answer and explain your reasoning. Now, let's think about situations where we could answer that question affirmatively, that it's plausible that there is a difference. If this confidence interval consisted entirely of positive numbers, then we would be 99% confident that this difference, since it lands in that interval consisting only of positive numbers, we are 99% confident that this difference is positive. If this interval consisted entirely of negative numbers, we would have a high level of confidence that this difference is negative, and therefore there is a difference between these two. Unfortunately, this interval contains both positive and negative numbers, and so we cannot distinguish between these two parameters at the 99% confidence level. Now, it is an interesting question, right? What would happen if we exchanged a 99% confidence interval for a 95% confidence interval? Now, that would manifest itself in changing out the 2.576. We would change out that 2.576 for the significantly smaller 1.96. That would almost certainly change this into an interval that consisted only of positive numbers. And at 95%, at the 95% confidence level, we would almost certainly be able to say that PM minus PF is positive, and that the proportion for men is therefore greater than the proportion for women. Okay, so that's basically how we have to conclude part two. At 99%, at the 99% confidence level, we can't necessarily claim that these are different from each other. Okay, so that brings an end to section, or problem 5.52. Now, there's one last thing I want to talk about, and that's margin of error. So let's go back to the slides. Okay, so one last thing we want to touch on before we close section 5.2 is we want to have a little bit of discussion on margin of error in our confidence intervals. So, when we're trying to construct, or when we're constructing a 1 minus alpha confidence interval, we know that our interval is going to be centered on our best estimate, but we're going to subtract and add z sub alpha over 2 times SE. So the radius, so to speak, of our confidence interval is being determined by the product of z sub alpha over 2 and this SE. And that product is called the margin of error. It tells us how it's going to determine how wide our interval is or how narrow our interval is. All right, now let's think about this. If you want greater confidence, so let's suppose you move from 90% to 95%, or from 95 to 99%. If you want greater confidence, the margin of error must increase. Why? All right, let's see if we can explain that. So if we look at our margin of error, we can see where our confidence level is coming in. As our confidence level goes from, let's say, 90% to 95%, or from 95% to 99%, this value of alpha is going to have to get smaller, right? Because alpha is in some sense telling us the amount of stuff that's being left out. So at 90%, alpha is equal to 10%. And at 95%, alpha is equal to 5%. So as I increase my confidence level, the value of alpha, the bit that's left out, is getting smaller. And as this number is getting smaller, that z cutoff has to be pushing further to the right. So this number is getting bigger. All right. And that means that everything else being the same, my margin of error must increase because I'm increasing the size of this multiplier out in front. So as I move from 90% to 95% to 99%, my margin of error has to be going up. All right. This is kind of a preview of what's going to happen in Chapter 6. We're going to delve into some more theory in Chapter 6, but as we will see in the next chapter, the SE of the Bootstrap dot plot will get smaller as the sample size increases. So one way to affect the size of the SE is to work with bigger samples. So in other words, increasing the size of the sample will decrease SE and hence decrease the margin of error. So if you want to affect the margin of error, make it smaller, but maintain a certain confidence level. So keep this fixed, but make the margin of error smaller. One way to do that is to make the sample size bigger and bigger. So getting larger and larger samples should increase the amount of information you have about your population. It should give you more information about your parameter that you're studying, and it therefore should give you a smaller margin of error. All right? Increasing the amount of confidence that you want to have in the estimation of your parameter, however, works against you in this case. It makes the margin of error bigger. All right, so hopefully that's a little bit on the margin of error that will help you how to think about that correctly. All right, so more on how the sample size affects the standard error when we get to Chapter 6. All right. In the meantime, I hope that you got something out of this video lecture. Work some problems from section 5.2 to see how things are going. And we'll talk to you later. All right, take care. Bye-bye.